So hello everyone. So in this session we'll start the analysis of recurrence equations, or sometimes they are called as recurrence relations or something like that. There are different names which are given to it. So we'll start our analysis on that, and this is the continuation of our topic of time analysis, time complexity analysis. We'll change the pen. Time complexity analysis. Just a bit of revision. So what we did so far is we learned different types of functions and different types of order growth, and we saw what are asymptotic notations. Now, but there are some algorithms like divide and conquer approach are there, in which an algorithm works on that. So it divides the problem and then does some work in the first division, and after that it keeps on dividing the problem till it gets to some base case, and then it again conquers the algorithm. So such algorithms, these algorithms, they form what is called as a recurrence relation. So one step is basically dependent on the previous step. So that's the first thing I would write here. Recurrence relation or recurrence equations. So how do they form is, so when you have algorithms like divide and conquer, when you have some, like let's suppose one algorithm is merge sort. So merge sort, what it does is it splits the problem. If you see in binary search, what is that? So it splits the problem into half. So when some algorithms are like that, which split the problem into some parts and then try to again split it back until it get to some base case and solve the base case and go upwards like that. And there are some algorithms, for example, like Fibonacci series. Okay, Fibonacci series, what it does is the output of first step is dependent on the previous steps. Okay, and that is where these relations recurrence relations come to play. So they play a significant role in optimizing this algorithms, because sometimes we have recursive algorithms also. So in recursive algorithms we also use these recurrence relations. So first we would see what is a recurrence relation. In nutshell, I would like to give you a definition. So recurrence relation or equation, so they are mathematical equations. Basically they describe a function or a sequence of terms in its previous values, in terms of its previous values. So in the context of algorithms, so they are commonly used to analyze the time complexity. So how is the formulation? So something will be like this. So let's suppose t of n means time taken on input n. So when you have n input, so this is the time taken. So it will be something like this: t of some g of n. So some other function will be here. Okay, like this: t of n is equal to t of n by 2. Okay, plus some f of n will be also here. F of n means like what is the work that was done in the step, and here let's suppose is n square. So this is an example of a recurrence relation. So if I just write a definition in quick, so it that by it I mean recurrence equation. It expresses the value. It expresses the value of a at some point function at some point in terms of its value at one its value in terms of its previous values at one or multiple points. Okay, this is sort of a vague definition. So if you see Fibonacci series, so in that you write something like this: Fibonacci of n is equal to fn minus 1 plus fn minus 2. So you know what Fibonacci series is. So it starts with 0, then 1. These are the first two terms. Then you add these two terms to get the third term. So this is 1, and then you will add these two. You will get 2. You'll keep on adding these two terms. So now you'll get 5 and so on. So here if you see, this is its recurrence equation. Now the current value is dependent on 2 points. So it's n minus 1 and n minus 2. So that's what I meant by here by the definition. These recurrence relations, they express the value of a function. So here if you see, this is a function value f of n. So the express value of function at some point. So at this point means at the current point. So here we have this current point n. So how do they express it? They express it in terms of the previous values. So previous values at one or multiple points. So here we have 2 points. So it can be even 1 point only. So I just gave you one example of Fibonacci series. So why do they occur? So I told you they occur in divide and conquer algorithms. So we'll have a detailed discussion on these algorithms in the future. So these algorithms, so when you solve problems by using divide and conquer algorithms, so you will see that these algorithms, when you analyze them, so it's easy to analyze them by using these recurrence relations. And the second thing is, where will you use them? If you have a recursive algorithm. So again, it's a huge topic. Recursive algorithm is a huge topic, so there will be recursions. We'll talk about these things, and there you will analyze these algorithms by using these recurrence relations. So relations will be of type something t of n, that means time taken when the input is, and if the problem solved it like t of n by 2 plus order n, something like this. It will be something like this, and you will have to solve these relations. I hope the concept of a recurrence relation is clear. Is it clear? So there are different types of recurrence relations. So I'll just name few of them. So types of recurrence relations. So the first type of recurrence relation is linear recurrence relation. Okay, so we have linear recurrence relation. I'll write RR for the short form for these. So following some of these examples, if you see, let's suppose we have an example of a recurrence relation like this: t of n is equal to t of n minus 1. You see the linearity in here. Okay, so they follow the linear rule, so they are called a linear recurrence relation because we don't get some other function in here. So these are linear recurrence relations. So we won't have a detailed discussion on these because otherwise the whole class will go into just explaining what are different types of these things. So I'll just name a few of them. So one is linear, and then we'll have divide and conquer recurrences. The second we'll have divide and conquer. Then we can also have something called as homogeneous and non-homogeneous. And there are substitute and there are a lot more other than this. So we don't care about what the types, and I just wanted to wanted you to know the names of these because they'll appear. And once if given time, and we'll solve the some of the relations mathematically if we found time, and some algorithm if they are a little bit complex, and if they require some attention, that time we'll go into the mathematical details of these things. So let's first see how to solve. There are different ways to solve the recurrence relation now. So what are different ways to solve? So if you got a recurrence relation, so what are the ways to solve? Okay, so that's that topic we'll cover now. So how to solve a recurrences? How to solve recurrence relations or recurrence equations? So how to solve them? There are a lot of methods. One method is called as substitution method. So one method is called as substitution. Why am I giving you all of these names? Because at least you will know these names, so that if you, even if we don't have a detailed discussion on these methods, but still you know, and if you sometimes have time and you can just search up these methods, and there is a lot of material available online or in the books where you can read about these methods. And the second method is Master's theorem. And then other method is a recurgent tree method. This is our main topic for today. We'll see how to use Master's theorem to solve the recurrence relations, because this is the easiest way and this is the most heavily used, and many of the algorithms that we analyze, they'll use this Master's theorem, and sometimes we may use some back substitution or recurrence method, recurrent tree method. You also should know these things. So first we'll see what is the substitution method. So in substitution method, if you have a recurrence, let's suppose if you have recurrence, so what you do, you take a guess. You take a guess, and then if you know about induction method, there are different types of methods by which you prove things. So one type is called as induction, prove by induction. So you try to prove it by induction then. Okay, that's one of the methods. So what do you do in the substitution? So in substitution method, you try to guess the answer. You try to guess the answer, and then what you do is, by induction. So there is a technique called by induction. Okay, by using this mathematical induction, you will try to prove your guess. If it is wrong, probably you will get the ballpark. Okay, I am wrong, I think it should be greater than this or it should be less than this. So you just change your guess then, and you do it iteratively, and you hit on the right guess. And sometimes what people do is they'll take a guess and they'll find the upper bound and lower bound. So in this substitution method, so what people do is, so one is using the induction, mathematical induction, to prove. They use mathematical induction. So if you have heard about mathematical induction, so there you take some base case and then you take some inductive step and you try to prove it, things like that. This is a whole topic in itself, mathematical induction. So you would make a guess and you do the induction. And second method is people try to compute upper bound and lower bound. So upper bound and lower bound is seen. This topic, this may seem vague because I am not giving all the details. The only point of introducing these topics is that you know these things, that these exist. But this is not our topic of the discussion. But in order to cover those things, I just am giving the context. So if you're not understanding, it's okay. Okay, if you're not understanding these things like mathematical induction, inductive step, what are these? It's all right. I just want you to maybe bear for a couple of minutes so that we just cover the context. So we'll get to the master's theorem. So what in this substitution method, we'll guess an answer, and either we'll use mathematical induction and prove that our guess is right or wrong, or otherwise what I have seen or what the different books present is that they'll check the upper bound and lower bound for your guess, and they'll see it does not follow the lower bound, and they'll again make a guess. So let's suppose they first guessed on L log n. So in n log n they found no, no, our function this is too much. So the complexity of this is not our tighter bound. So they'll guess n. Okay, so this they'll say, oh, this bound is very less, so they'll say answer will be somewhere in between this. That's how they adjust their guesses. So in the induction you will use mathematical induction, in this you will use this upper bound and lower bound. So this is one of the methods. So one method is substitution, and there are other methods to solve recurrence, that's called back substitution. So in which if you have to solve recurrence like this, t of n is equal to t of n minus 1 plus, let's suppose, plus n, something like this. So what you will do is you will substitute this, you write t of n is equal to, so this will be equal to t of n minus 2 plus n. So this n will remain as it is. So you'll keep on substituting this. Okay, something like, and then there will be some base case, that is, let's suppose t of 1 is equal to 0, some, or t of 1 is equal to 1, something like this. So you'll write t of n is equal to t of, this will be now n minus 3 plus n, and now these two n's, and you will keep on doing till you hit this base case t of n. This is called as back substitution. This is called as back substitution. These all these methods all are read in and the discrete mathematics. I don't want you to bore with these methods, but I hope that you got a fair idea of what these. So we start with what are the recurrence relations, or what are the recurrence equations, and how do they arrive, and why are they important for us to analyze, because there are different algorithms like divide and conquer algorithms, recursive algorithms, which give rise to these equations. So based on these, you always not might not have loops. So because we saw loops, in loops we just saw the operation, these are operations that did. But in these algorithms like divide and conquer and these recursive algorithms, we inherently give rise to these recurrence relations or recurrence equations. There you'll have to solve them. So I said how to there are different types of recurrence. After that I introduced, and there are, I just listed a few of them. So how to solve these? So there are methods like substitution method, in which you guess the answer, and then either you use mathematical induction to prove your answer, or you use the upper bound and lower bound to find the ballpark of the answer. Okay, I don't think this answer is way above and this answer is way below, then their answer will be lying in between like this. And then there is master's theorem, that's our topic, and there is a recurgent tree method, and there will be other methods also. There are back substitution methods which I just showed you here. So this method is called as back substitution. So now the whole discussion is on the master's theorem. Okay, so what this master's theorem is actually, so what happens if these recurrence relation are of certain type, so if they follow a particular structure, then we have a theorem which is side of a cookbook for you. So you just if you have a dictionary sort of thing, so what you do is, you know a word, you'll just check the dictionary and you will find the meaning of the word. In a similar fashion, master's theorem is like your dictionary. So there will be if an equation follows that thing, and you will just check the master's theorem or which case does it belong to in the master's theorem, and you will say answer is this. So what is that thing? So if your recurrence relation is of the form, if it is t of n is equal to a t n by b plus theta of nk log Pn, and a is greater than equal to 1, b is greater than 1, k is greater than equal to 0, and p is a real number. If your recurrence relation is of this format, okay, where this t of n means time, or time taken on the n input. If it is like this, so if it is divided by something, and this means the problem is divided into like n by b, and then we have some factor a over here, and then we have some log of k. I'll just write it over here, n of k, log of p, and log of n to the power p. And then if these constraints are respected, this is one constraint. So if you see, this is one constraint, this is other constraint, this is the other constraint, and this is other, these four constraints are respected. So many of the recurrence relations you will find in real time are like this. Okay, they follow this format. So if a recurrence relation is of this form, then we can use Master's theorem. So what I said about Master's theorem is like a cookbook. It's like your dictionary. We'll just see what is the value of a, what is the value of b. If I write like this, t of n is equal to 2t n by 2 plus theta of n, let's suppose. So is it in the form of a Master's theorem? Yes. Why? Because here a is equal to, and that is a is greater than 1. This is actually greater than equal to, I suppose. Yes. So this, if you see a is equal to, and here this is n by 2, and sometimes you'll see it n by 2. So here also you see b is equal to, so b is greater than 1. So now here we have n, so n to the power k, k is equal to 1, p is equal to 0. This is of the form from the Master's theorem. So if you see, this actually follows this Master's theorem form. So that's, these are the values, and they also follow the constraint. Are you able to understand this? Waiting for the answer. I cannot see the screen.
Yes, sir.
Okay. So what I said is, Master's theorem is like your cookbook, it's like your dictionary. If a recurrence relation or a recurrence equation follows this format or is of this form, then you can use the Master's theorem. Let's go into the Master's theorem. There are different versions of Master's theorem, and I'll introduce one of them, and which is the easiest to understand. So I'll just paste an image over here. So this is what Master's theorem is. Okay. So the first case is, if this a is, if you see over here, if this a is greater than b to the power k, so now you have b, you have k, you have a also. If you see that, this is case 1. If a is greater than b to the power k, then the answer is directly this. Then this is the answer. Theta of n log ab. This is the answer. In the second case, what you see is, if a is equal to b to the power k. This is the second case. So then in there we have sub cases. Now we will see p. In the first case we don't see p. We only see a and b. The first step is to see a and b. So if a is greater than b to the power k, if this a is greater than b to the power k, so what you will do is you will directly use this formula. But in the second case, if a is equal to b to the power k, if these two are equal, a is equal to b to the power k, then what you will do is you will see now the value of p. Okay, now p, you know, is a real number. P can be uh, positive, negative, or it can be 0 even. That's how we see. If it is greater than -1, so you will use this case. If it is greater than -1, you will use this case. If it is equal to -1, you will use this case. If it is less than -1, you will use this case. And then the third case is there. So what is the third case? The third case is if a is less than b to the power k. This is the third case. Then what you do, there again are two cases. You'll again go resort back to p. If p is greater than, if it is positive, that p is greater than equal to 0, then you will use this. Or if p is less than 0, you will use this case. Here you don't have to memorize this. You can easily grab up this sheet of Master's theorem, or even you can take a screenshot of this, and then you will be easily able to solve the things. So let's now do some problems on the Master's theorem to show different cases. Okay, so let's do one of the problem. So if, let's suppose, t of n is equal to 3t n by 2 plus n square. Okay, let's suppose this is our recurrence relation from any algorithm. Now here you know the first step that you have to do is if it follows the Master's theorem form. Yes, it does. Why? Because here you can see that a is equal 3. Okay, then b is equal 2. Okay, a is equal to, here is this a is equal 3, b is equal to 2, and then k is equal to 2 and p is equal to 0. Okay, now we'll check the case. What we'll check? If a is greater than b to the power k. What is a here? 3. Is it equal to b to the power k? What is b? B is 2. K is 2. 2 to the power 2. So we found that 3, 4. So is 3, this is less than 4. So a is less than b to the power k. So a is less than b to the power k. So where is it? It falls under this case. Case 3. A is less than b to the power k. Now we'll go to the p. If p is greater than equal to 0, then we will follow this. Otherwise, we'll go this. Here k p is equal to 0. So it follows in this 3a case. So what is the answer directly? Theta of n to the power k. K is 2. Log of p is 0. N. So this is theta of n square. Okay. So how many of you understood this example? So what I'm saying is Master's theorem is like your cookbook. So if a certain recurrence relation follows a particular format that is in the Master's theorem, you can directly look at the cookbook and see the answer. So it's like a dictionary. If you have a word and you just open the dictionary, see the word and corresponding meaning is there. So that's what that is. So if your recurrence relation is of this form and it follows this form, then you can use this cookbook. So here we have three cases first. This is case 1, case 2 and case 3. We check this a is greater than b to the power k, or a is equal to b to the power k, or we check a is less than b to the power k. These are the three cases. Then we have sub cases. So if I give an example of this recurrence, let's suppose we'll take an example of some other recurrence, and I'll just copy this Master's theorem, because I even myself do not memorize this relation, this Master's theorem. So this is our Master's theorem. Let's put it here. Okay, now we'll see some other example. Let's suppose our recurrence relation is t of n is equal to 4t n by 2 plus n square. This is the recurrence relation. Okay, now we'll see if it follows Master's theorem. So this is the format that it should follow. A should be greater than or equal to 1, b should be greater than 1, k should be greater than 0, and p should be real. So now here if you see a is equal to 4, a is equal to 4, then b is this n by b. So n by b, this is b. So b, if you see over here, is 2. B is this, and then we have this n to the power k log of pk. Now k is equal to 2 and p is equal to 0. These are the values. So if you just compare this recurrence relation with the generic format of the Master's theorem recurrence relation, you will find that these are the values of a, b, k and k and p. So and all of these will follow the constraints. Now we'll have to just find a and b to the power k, and then we'll see the relation. What is a over here? A is 4. What is b to the power k? So 2 to the power 2. This is again 4. Now you saw that a is equal to b to the power k. This is what you saw. A is equal to b to the power k. This now follows this case 2. Okay, this is our case 2 over here. This is our case 2, because a is equal to b to the power k. Now we'll check for the p. If p is greater than -1, we'll check this. P is equal to -1, we'll say this. P is less than -1, we'll see this. Here p is equal to 0. Okay, that means p is greater than -1. So we'll check this case. This case will be followed. So the answer will be this. This is the answer that we'll have. So the answer will be theta of n log n to the power log ab. And what is a here? 4. What is b here? 2. Then log of p plus 1. P is 0, 1, n. So we'll just simplify this. So theta of log, I think this should be n square, because log 2, 4 means 2 to the power 2. So this get cancels and this will go up. So that's why I gave you the formulas for the log. So this is n square log n. So this is the answer. So how many of you understood this now? Just help me. So what is a equal to here?
Sir, A is equal to 1,
Okay, b is equal to
2,
okay, k is equal to
K is also equal to 2.
2, p is equal to
Sir, P is 0.
p is 0. Now you see the first thing that you have to do is, if given this recurrence, let's suppose this is your question. Now you will find these constants and you will see, does it follow the recurrence format that is given by the master's theorem. Okay, that's here we have written that. You just check with it. And here a is greater than equal to 1, b is greater than 1, k is greater than equal to 0, p should be real. I think it follows all the constraints. Now we'll check a and b to the power k. Okay, what is a here? 1. Amir, what is b to the power k?
Sir, it's 4.
It is 4. So here now 1 is less than 4. Okay, so which case does it belong to? Case 1, 2, or 3?
Sir, sir,
Eh,
it belongs to 3.
So case 3. So it belongs to this case. So this is our case which it belongs to, third case. Okay, so now we'll go to the p. So in which case does it belong to? P is equal to 0 now. So it belongs to
Sir,
3a.
first one, yes, sir.
3a. So this is our case. So now we'll directly take this answer. So if you see, we'll take this answer. So what is this? This is theta of n to the power k. N to the power k is n to the power 2. Log of p means log of 0, that is 1. Log of n raised to power 0, that's 1. So this is our answer. I hope that you will be able to answer this recurrence relations if they are in the format of Master's theorem by using the Master's theorem. Okay. Now we'll move on to the next topic, and then there is tree based method. So again, if you remember the graph, so what I told you is the first thing that we studied about is recurrence relation, what these are. Then I said what are the types of recurrence relations. So there are different types of recurrence relations. Okay, then based on these types, what are the things that give rise to these? So I said different types of algorithms, that divide and conquer recursive algorithms. These algorithms give rise to these. Then we saw different methods which you can use to solve it. Different methods to solve recurrence recurrence relations. Then you had some methods in which we had substitution method, we had master's theorem, and then we had this tree based methods. So we covered master's theorem among them. This is the whole graph till whatever we understood so far. Okay, I just give an introduction of tree based methods also. How do they work, tree based methods? So in tree based method, you basically construct a tree. So if you have a recurrence relation, let's suppose like this: t of n is equal to 2 times t n by 2 plus n. So how do you say? You say, let's suppose this is root. I'm solving the problem t of n. So this gets splitted into t of n by 2 and t of n by 2. That's what is the meaning of t n by 2. And each the step takes order n time. So again, you will now split this. So this will get split to t of n by 4, t of n by 4. Okay, same here. T of n by 4, t of n by 4. So each of this will take time n by 2 now, because if on this n it was taking n, so on this n by 2 it will take n by 2 time. So but for this it will take n by 2, and for this it will take n by 2. So each step will again take, this will again take n time. So okay, and you will have to see how much time does it take. Okay, how much time does it take it to get to the t of 1, let's suppose base case, and you will count this how many n's are there. Okay, something like this. So this is called as the recursion tree based method, or you construct a recursive tree and then you compute this number of steps. Again, we'll have a detailed maybe discussion on this once we have some algorithm in which we'll use this tree based methods. And there are a lot of methods to solve the recurrences, but one of the most important method that we covered is master's theorem method, because I'll say somewhere around 60 to 80% of recurrence relations of the format which follow the master's theorem. Okay, that's why I wanted to have a discussion on this. And there are other methods also. There are some peculiar methods which solve a very less class of recurrence. Let's suppose 1% of recurrence relation, they are really hard to answer, and that time we have different methods, and these answers are asymptotic answers. Okay, there is some answer called as closed form answers. So what is a closed form answer? So closed form means give the exact answer. So if you have a recurrence like this, t of n is equal to t of n by 2 plus n square plus 4 and something like this. If you have something like this, so maybe you can give one asymptotic answer, and one answer will be you can give exact answer like this. So the answer will be, let's say, n square plus 2n plus 4 divided by 6n plus 20, something like this. This is called as closed form answer, where you exactly give the answers. You don't give just the ballpark. You don't use the asymptotic notation. This is called as closed form, and you will frequently see this when you once you do the advanced course on algorithms. There they don't ask only the answers of this asymptotic answer. They sometimes will ask you give the closed form answer of this, and there you will have to use a lot of mathematics, and there you will have to use a lot of what you studied in algebra and what you studied in your lower classes, and you will come up with these closed form answers. Is it clear?
Yes, sir.
So now you understood the master's theorem. So now first thing that I would like to say about the master's theorem is that it is just like a cookbook. Do not use it for every recurrence relation. So please and please see if it follows the format of the master's theorem. Okay, and then only use it. Otherwise, it'll be a disaster. So now we'll go on to the next topic, that is amortized analysis. What is this amortized analysis? So sometimes if you see, there are algorithms or there will be some operations in within an algorithm which takes less time, and some operations will take more time. So there what you do is, even if you have an example of hashing, I don't want you to give the terms which we haven't introduced, but still I'll give some example. Let's suppose we have an algorithm, let's call it algorithm 1. It, let's suppose it supports, say, one operation called as insert. There is an operation insert. Usually what insert takes, usually insert takes order 1 operation. Okay, it usually takes order 1 operation, and but after a while it takes more time than this. Giving a physical example, let's talk about static array. So let's say we have an array and we insert in the array. So if you have an array of this, like for the first element, what you do is you will insert in the array and it will take just one time, one element. So the first, this is our first number of operation, this is our first operation. So for the first operation it took order of 1. Okay, now when you have to again insert it, because you just have the static array, now you'll have to double the array and then you do it. So what you do is you will make the array double and then copy this element over here, you copy the element 1 over here, and then when you insert something, let's suppose you insert 2 now, and you will insert 2 over here. Now you see this operation became costly. If you have the space in array, so that time what will happen is your insertion will take order and time. But if the array is full, if array is full, what will happen that time is you will have to first create a new array, then copy the previous elements in the array, and then now there is space, now you will have to insert the operation. So are you seeing insert operation behaves differently? So how many of you are able to see it, at least that insertion operation in the arrays, it behaves differently? So when the array is of size 0, first we'll create an array and we'll create a size 1, and this is about the dynamic arrays. Second time what we will do is we usually double the size. So we had one size and we double the size, we made the array size equal to 2, then we copied the previous element that was in the previous array, and then we insert the actual array. Now if you have to insert again the third operation, now the array is full again, now you'll double the amount of array, so you'll make it 4. Now you'll first insert 1 and 2 over here, now you'll insert 3. Okay, in the fourth insertion you will directly insert 4 over here in order 1 operation, but in the fifth insertion you will again double the array size. Okay, 1 2 3 4 5 6 7 and 8, let's suppose you'll double, and you'll now copy these elements 1 2 3 4. Now you'll insert 5 in the sixth insertion, 6 directly here, 7 directly here, 8 directly here. You saw most of the operations are taking order one time, but sometimes once in a while what happens is the operation takes more time. Maybe it takes order and time. In here if you see, it takes order and time first, because you have to create a new array, copy all these n elements, it takes n plus 1 operations. So what is amortized cost is, amortized cost says if there are some algorithms in which usually an operation takes very less time, but once in a while it takes a lot of time, then we can do an average analysis. What we can do is we can use all of this analysis and come up with an average score. Okay, this is what the time takes. So what will be the complexity of such n insertions if you see? So for the first item it will take one operation, for the second let's say it will again take two. So I'm saying the cost it takes. For the third it takes 3 because you have to copy it. Again for the fourth operation it takes 1. For the fifth it takes 5. Again 1 1, and sometimes till 9 it will take like this. Most of these will be, and you will see it will followed by a lot of ones now. So there will be a lot of ones because mostly it is constant time operation, but when you have double the array, that time it will take order and operation. So now if you have to compute the amortized cost, this is called as amortized cost. So what you will do is, so you will sum up all these numbers and divide it by the n. So it will be 1 plus 2 plus 3 plus 1 plus 5 plus and so on. So if you simplify this, so it will be giving you something like this: 1 plus 1 plus 1. So you are keeping these one separate, and then you are using these 1 plus 2 plus separately. So you'll be using 1 plus 2 plus 4 or 5, whatever this is, divide by n. Here it will divide by n. So now if you see, so it will come as n plus 2n divided by n. Okay, so if you see it over here, this is less than equal to 3, so this is order 1, this is constant time operation. So overall you see this is a constant time operation. This is called as amortized cost. Amortized is constant, but once in a while the operation was taking a lot of time. This I took an example of dynamic arrays, so where the array is continuously growing. How many of you understood the amortized analysis? This is called as amortized analysis. So again, in nutshell, I'll just like to brief it. So what it does is, so amortized solutions are the solution. They are the methods where some of the operations, when you do it, they occasionally take more cost, and for the majority of the time they take less cost. Let's suppose. So what we do is we efficiently amortize it, basically average it out. If you see it, I gave the example of this dynamic array. I hope this concept is now clear. So if you see the order of growth now, so I'll just plot a graph like this. So this is our order of growth graph. So what was in that order of growth? The first thing was constant time. So constant time means irrespective of how the input grows, it will be constant. So this is our constant time graph. This is our order 1. Okay, then we had log n. So log n was something like this. Okay, this was, let's suppose, order 1. This was our log n. So log n is like 1 after a while. So this is log n. Then we had order n. So order n is like this. This is order n. Okay, something linear. Then we had n log n. N log n is a little bit like this, a little bit upper, n log n. Then we'll have n square. N square will be quadratic, something like this, n square. Then we'll have 2 to the power n, exponential, 2 to the power n. Then we'll have a much worse case, n factorial. Then we'll have something like this, n to the power n. Okay, these are all order of growth. I showed you graphically how they increase with the increase in input. Okay, so just extend these so that they touch this point. So I just showed you the rough. This is our, let's suppose, rate of growth. Rate of growth. This is how different functions behave, and most of these, when you analyze the algorithm, they'll be either constant time, logarithmic time, maybe polynomial time, and then this polynomial, logarithmic, analog, and then even quadratic, cubic can be there, cubic n4 or something like this. Is exponential, factorial times n to the power n is the worst case that is possible there. So these are the order of growth, and all these tools can be used to analyze time as well as space. So I'll just brief you about space complexity also. Space complexity. So what is this space complexity now? What I said you is that when you analyze the algorithm, I told you the goal of this course is so that you design your algorithms. You don't only design the algorithms, but your algorithms should be efficient. So how is efficiency defined now? The efficiency is defined in terms of space and in terms of time. Okay, so how do we define the space? How do we define this efficiency? So efficiency is defined in terms of time, in terms of space. There can be also other metrics. How do we define efficiency? So efficiency you can also define how easy it is it to code the algorithm. Sometimes the algorithm is really good, but it's really hard to code. Okay, and maybe we can say coder's ease. But we don't take care about these things. We assume that coder will know how to code the things and programmer will know this. So usually these are two metrics we'll use. We'll use time and we'll use space. Again, to reiterate, I am not here to teach you the things. Like, I'm not here to, I'll tell you these are the things. These are things that are written in a book. I'm rather teaching you how to think. So that's what I'm coming up with this. The efficiency, if you see from the real time perspective, let's suppose you are having a problem something and you are saying I need to compute efficiency. So how to compute efficiency? Maybe time and space cannot be the factors there. There will be something else. Let's suppose there can be some other metric, use of materials. So that's efficient. If you are designing a car, so you are saying what is efficient over here? The efficient car is if its speed is very high. Okay, speed is very high. And then what's the other time, how I can compute it? It's an efficient if it, let's suppose, uses very cheap material or something like that. That's what by efficiency mean. In terms of algorithm, what's the meaning of efficiency? The meaning of efficiency is if it uses less time, less CPU resources. Okay, because time is directly proportional to the usage of resource. How much CPU does it use? And then we have space. How much the physical RAM or physical storage does it use? Because we have CPU and we have memory. These are resources. These are two resources, like important resources. Monitor and also like CPU. If it uses a lot of CPU, it uses a lot of power. If it uses a lot of memory, it also uses a lot of power. Okay, then CPU won't be able to do a lot of things. So there are a lot of repercussions what you see. So some algorithm, if it takes a lot of time, then it obviously means it takes a lot of power also. Okay, because power means by power I mean the electricity will be consumed a lot. So that's how you see the efficiency. That's why we only quantify these two things, time and space. But underneath the hood, you know that what is the repercussion of these things. If an algorithm is taking a lot of time, that means it is taking a lot of compute power, a lot of computation is being used. If it's taking a lot of computation power, that is power drained by it will be very high. Okay, and it will this algorithm is not efficient. It is better to have sometimes some error in this algorithm which gives some error, but it takes very less time. Okay, then the second thing is space, because space is a constraint, because we have limited memory in our computers. So you'll have to take care of the space. If something takes a lot of memory, that means maybe it cannot fit within the memory, and we'll have to come up with different methods and things like that. So is it clear how do we quantify this efficiency? So we quantified it based on time and space, and now we'll have to measure this time and space. For that, we'll learn about the analysis. We'll learn about asymptotic notations, best case, worst case, and things like that. So time, you can see now, if you see the instruction level, we saw how to compute for the for loops, recurrence relations, and things like that. Now we'll go into the space, how to compute the space complexity, how to compute if an algorithm uses more space, is it efficient space wise. Okay, so how to do that now? Now in the space complexity, what you see is, you see how much space does your algorithm take. Okay, it is the amount of memory your algorithm takes, amount of memory algorithm takes. This is what I mean by space complexity. So there are various factors that even contribute to their algorithm. So for example, even sometimes when you do some things and you use additional memory to store something, let's suppose you are using swap. If you know about swap operation, so you have, for example, a is equal to 1, b is equal to 2, and you want to swap these two numbers. Sometimes there are algorithms to swap where you use a third variable. You'll say I want to swap something, so I'll use c. Initially I'll temporarily store this 2 into this c, and then I'll replace this with 1, and here now I'll replace this with this, and now you use extra space in here. Okay, for the swap operation. It is just a vague example, because in algorithms sometimes they'll use a lot of space for temporary computation or something like that. So this is that's the space we will take into consideration. Okay, what is the extra space it's using? Okay, and there is fixed space sometimes. So what, any algorithm, let's suppose it takes that space. Let's suppose I wrote an algorithm, so I said there are different factors, so I'll write it under factors. So what are the factors that are affecting the space? The first is fixed space. So what is meaning of the fixed space? Okay, so if you see an algorithm, it depends on fixed number of variables, because you are writing something, you are initiating a for loop. Obviously that I is equal to 0, I is less than equal to n I plus plus. This is some sort of fixed, because you cannot take it away from the algorithm. If you are running a loop, or if you are declaring some variables, anyway these variables will be sort of squashed only when the algorithm is done. That is some sort of fixed space, you cannot do anything with that. Okay, this is the space that it will be a variable space. And sometimes what the space, the other space can be, is fixed, and then we can have variable space. So what is variable space? Let's say if it's a recursive algorithm, it will take stack space, so it will have to make a lot of function calls. So that time, some algorithm, if it runs on some input, so what will do, if it runs on, let's suppose, n input, it will have n calls. If it runs on 2n input, it will have 2n calls, something like this. So you see that based on the input. So in the fixed space, if you see these variables are there, so they anyways won't get changed, so they'll have fixed space. And then when you make some calls, recursive calls, each call is taking some space in stack. So when you take a variable size input, then your calls will be varied. So that's why I call them a variable space, because it takes a varied space. Then there is something called as auxiliary space. Sorry for the spelling, really bad at spellings. So auxiliary space, so what is this? So if an algorithm requires additional space beyond the input size or temporary state, okay, so what it does, it has to temporarily store something, temporary storage. So that I showed in the swap case. So when you do something and at that time you have to store something temporarily, that's called as auxiliary space. And these are the factors that contribute towards the space. So one is fixed space. That means these variables, whatever the algorithm has, we keep count of some things. You introduce some variables, or you introduce some array of some things. So that time, to store something like to so that algorithm runs, this is in the fixed space. Then we have variable space, in which the algorithm space shrinks or grows based on the input. Like I said, in terms of recursive, we have to make different function calls. Even in other examples, so for example, if you have n square, if you have an algorithm n and it takes n square space, that is the variable space. And the auxiliary space is when some algorithms they store something temporarily. They don't use it everywhere, but they have to store something temporarily. But all these factors, they contribute towards the overall space complexity. Okay, overall space complexity. There are other things that you will have to analyze where seeing. You first will see these order one, because you won't take them. You will see, okay, because we don't need to take them because they anyways will be present there. But you will have to see these two things: if it is using some auxiliary space, if it is using some other things in there, if it is using some variable space. I gave an example of this swap, and let's see. Let's suppose we'll take an example of sum of elements. So if you are taking an array and you are summing up all the elements, so there you will take order and complexity. So you will, for example, you have an array. Let's suppose this is an array of elements in which 1 2 3 4 5 6 elements are there, and now you'll have to store this array somewhere. Okay, usually there are two, I'll say, schools of thought and also there. So sometimes they say whatever you give the input, it should not be considered in the space. But some people say that you should also consider it in the space, because it obviously has to store in the memory. Okay, I belong to the latter part. I consider that if the space, if the input that you are giving is taking a lot of space, then you should take into the time complexity. It is not only the what is happening within. Okay, it's also take the input also in the space complexity. But there are also other people that won't take this as in the consideration. They'll say, okay, this is an input, I won't take this into the consideration of the algorithmic analysis. But you can see both the things. Anyways, you'll have to analyze the algorithms. You can choose to be on either side. You can choose to be, say, let's suppose you are saying that I won't take the input size in my space complexity. I'll see what happens inside the algorithm. That's also a good thought, because we want to analyze the algorithm only. That's their point. Their point is that if we're analyzing algorithm, there is no point in taking what input it takes. So input anyways you have to give it. And second school of thought says, but input still has to reside in the memory. You should also consider this in the algorithm itself. So if input is reside in the memory, so it makes sense to keep it in the space complexity. But you can choose to be on the either side. So I'm saying, if you have an array, let's suppose, and you are computing the sum of this. So if you are computing sum of this, so you'll have to take each of these element. Okay, take each of these element. So if you do not take this array as in the space complexity, so it will take order one time. Why? Well, it will take order one space, sorry. Why will take it order one space? Because it will read each of these elements. Let's suppose this is our algorithm. This is our algorithm which takes this as input, and then it sums up the elements. So it will copy each of the element in one variable. Let's suppose there is a variable sum which is initialized to 0. Then it says a, or maybe sum is equal to a is equal, let's call this array. So this is our array. First it will copy this, it will read this array of I. Okay, array of, it will run loop along this. So then what will it do? It will store this element array of I into a, and then it will say sum plus equal to a. So just add this a into the sum. So add this a into the sum. So what it is doing instantly, so in one iteration it is using this a, it is using order one space, and in each iteration it's again reusing the space. So it is not giving you more space. So you can say this is a constant time algorithm in terms of space, because this is irrespective of howsoever this array grows, because nowhere we are using additional space. But if you are from the latter approach, if you say that this array size, you'll have to store it in the memory, because you read it somewhere, the algorithm tries to read this, and if you consider, then it's order n algorithm, order n in space. It depends how you see it. If you see that the input I won't use in the calculation of space computation, then it is an order n space or order one space. Why? Because it just stores into this a is equal to this array. This each element of array is stored into this a, and then it use it for the computation. But if you use the approach where you take the input into consideration, that input resides in the memory, then anyways it will have to use order and space. Okay, and then let's suppose you are creating a matrix. Okay, this is order. If you are creating a matrix, let's suppose you are filling a matrix. You are creating a matrix. Creating a matrix. So what is the meaning of creating a matrix? So you are creating something in like this. Okay, and you have to create, let's suppose 1 2 3 and up to, let's suppose, 10,000. So if you are given input, make a matrix, and the values in the matrix should be let's suppose 1 to 1000, something like this. 1 to 1000. So 1 to 1000, but you should fill all of these values. You should first take 1 2 3 and then maybe square these things. So what will you do is you'll create a matrix and then keep on filling these values. So the size of this matrix will be the space complexity. If this is over here is, let's suppose, n, and if it here over is n, so total space will be order n square, something like this. So now I gave you the brief framework. So again, to just summarize it, what we discussed, to summarize it, the first school of thought is that the input should be taken into consideration while you are computing the space. Okay, input should be taken into consideration. And sometimes it makes sense. For example, we recently read an algorithm in data science that's called knn. Okay, that time it made sense. Sometimes it does not make sense. Anyways, you'll have to use the input, and this is the most accepted and most prominent. Input should not be considered. Input should not be taken into consideration. Okay, it should not be taken into consideration for the space complexity. But if you take it, so what are the factors that affect it? There are three factors that we just saw. First factor is that there will be these variables which are order 1, and then there will be variable space. Variable space means where, for example, in the recursive call, if you have to do some additional things which depends on the input, then there are auxiliary space which the algorithm itself uses for the space complexity, and it uses it to store something temporarily or something like that, and there we'll use these things. And now I hope that you can analyze these algorithms. So here now the two things that we analyzed is time and space, and all the tools that we studied for time, the tools, let's suppose, for recurrence relation, and the tools that we saw for these loops, if else statements, we saw these rates of growth, asymptotic notations, all of these apply here also. So both of these things are same in those aspects. But how do you analyze? It's a little bit different and a little bit tricky when you analyze these things. And we can just stop the recording of this over here.